Good. Okay. Okay, so we're on page 304, section 6.2, and it's got a strange title. If you turn back a page, it's called The Natural Base E. There are three very, very famous irrational numbers, and they are constants. And you're running into the second one today. Does anybody know the first irrational number that everybody's supposed to know about? Pi. The square root of what?
Not X.
Nope, sorry. Square roots are irrational. Lots of them are irrational if they're not square rooting a perfect square. Or if a cube root is not cube rooting a perfect cube. Anything that's not, doesn't fit into that where it comes clear out of the exponent, they're always irrational, and they are, there's a lot of them, so they're not too special, but thank you for that. That's good. Somebody mentioned the famous irrational number that you're supposed to know about by now. What is it? 5, 3.14159, blah, 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 forever and ever, never, 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 right? Today you're going to learn about another one, the natural base E. When you see a little e, lowercase e in math, it's got a very, very important meaning. Base of a growth model that happens naturally. Like the population of a bunch of rabbits. We all know that rabbits proliferate, right? And in the world we live in today, it's pretty clear that people proliferate. They also grow with a natural base e to the exponent. There is a third irrational number, which we may have time to learn about in this class, and maybe not, but you will learn about it sometime if you keep going in math and go to college. I just want to show you this. A friend of mine who knows I'm a math nerd found these for me. And just to redeem Colleen a little bit, there used to be 4. When I was bringing it in, I had a load of stuff and it fell right on the corner and busted the square root of 2. But this is, well, here's pi. And it's kind of funny, it's sort of kind of funny, because if you go into a bar and order scotch or whatever in one of these tumblers and you want pi worth. These are known as fingers. Well, sometimes these are kind of small fingers, but if you say 4 fingers of scotch, you're asking for a lot. 3 fingers, 2 fingers. Usually 1 finger of scotch is about 1 or 2, about a regular one. You go in and ask for pi, then they would fill it to here, of course, because that's 1, 2, 3 and a bit. If you go in and ask for, okay, I want E worth of gin. Or rum, whatever. This would be where they would fill it up to. And it is 2.718. You'll learn that today. You're going to write that down. I see some of you starting to write. E is approximately 2.718. Just like pi is approximately 3.14. And the last one, which we won't learn about today, but you probably will somewhere in your math career, this is a Greek letter rho. I know it looks like P, if you really use your imagination. It's a little bigger over here. And it is the golden ratio. And you don't have to write this down, but it is 1.618. There's your 1 point, a little more than half. So rho won't get you quite as drunk as pi. Okay? All right, and E is somewhere in between. So we've got 1.6 something, and we've got 2.718, we got 3.14. And the square root of 2 is 1.41, so it's in here somewhere too, and that's the last one. I mean, kind of sad. But if any of them had to break, that would be the one. These are, I love these things. They're so fun. So I got all kinds of math things over here.
If you're in a bar, do you really think they know how much to
No.
fill it up? Okay.
No,
That's what I thought.
That's the reason why it's funny.
I'm pretty sure if you ask somebody
It's like walking into Harbor Freight, well, not Harbor Freight, but walking into Cal Ranch and say, I got a gate I'm building and I need a 2x4 that is the square root of 78 inches long. Because that's what your Pythagorean theorem told you, when you figured it out, and they go, yeah. In reality, we don't use irrational numbers much. But when you're calculating something that has to be really, really, really close, we do use them. Okay. All right. Anyway, so 6.2, the natural base E. And it means base. It's the base of an exponent. So while we started out like this yesterday with a y equals ab to the x, where this was the beginning amount, this was the factor, the growth or decay factor that we were going to use over and over and over and over again this many times, producing a new number each time. Now today it's going to look like this: y equals ae to the x, where that's a very, very specific number, 2.718. Okay, and the reason they use E is because it's for one of the most famous mathematicians ever. In my world and what I know about mathematicians, he's the best guy ever.
Is this the guy you have a crush on?
No, I don't have a crush on him, but I do respect him a tremendous amount because he's dead. I don't have a crush on him. His name was Leonard Euler, and his name is spelled E-U-L-E-R. And it is not Euler. You will definitely expose your ignorance if you pronounce his name Euler. He's a Swiss guy, and it's pronounced Euler, like this. Okay? It's pronounced Euler, but it does start with an E, and he is the one that did all of the work with E to where we are today. His name's Leonard Euler, and the reason I like him so much is because...
Can I have your attention when you get all the choirs to go to the music room at this time? All choir students, please go to the music room.
Okay, what you miss is your problem, but it'll be recorded. Okay. Please don't trip on the ladder or the cord on the way out so you mess it up. Just don't touch it. The reason I like him so much is because unlike many other mathematicians and scientists, I don't know why, maybe it's just men in general, I don't know. But he married one woman, stayed with her all his life, had 8 children, was a very dedicated father, so all of their futures were taken care of. And he did math and worked out math and solved problems for kings and queens all over the world. And when he was dead and they finally gathered all of his new mathematical work together, it was over 40 volumes. More than I can reach in paper. He was very awesome mathematician, very, very humble. He is not the one that said, we will call this E because of me. He never said that. As a matter of fact, he balked against it. It was his peers throughout the world that said, look, you did this. We're going to call it E after you. He goes, oh, I really wish you would. He was very humble, very good father, very devoted husband, very awesome mathematician. All the things that I value. He was cool. See you guys.
Yeah.
Have fun singing.
Thanks.
I will.
Is that the guy with the temperature?
What's that?
Is that the guy with the temperature?
Oh, no, that was
He found out imaginary numbers.
Fahrenheit was a great guy, and he and his wife got along really, really well, but he was kind of a goofy. He was so anxious to publish, he totally forgot how to be a scientist. All right. He was Norwegian. All right. Anyway, moving along. Let's do some math now. And I'll try to get through this quicker now that I've done all the background stuff and all the things I like to say. Okay? Do you recall yesterday this equation where we were talking about money? I just had it on the board over there. Remember that?
Yeah.
Okay, now this is a very, very loose relationship, so don't expect it to work out exactly one for one. But this resembles this idea right here. Sort of, kind of looks like that. This piece right here. This is irrelevant. Doesn't matter how much you take to the bank. It's this part right here that makes it grow, your money, right? This part is your 1 and your plus, and then there's something here that got switched, and there's something here that got switched a little bit. But I want you to think about this for just a minute. N is the number of times you compound a year, right? If N is 4, then it's quarterly. If N is 52, then it's weekly. If N is 365, then it's daily. You can figure out the number of hours in a year. What I'm saying is, the smaller the time the smaller the amount of time, the bigger this number is. If you let this go to infinity, in other words, you compound every minute, compound every second, then you compound every tenth of a second, every picosecond, every nanosecond, you'd be compounding every instant, wouldn't you? If we let n get bigger and bigger and bigger, that's more compoundings per year. If you let it go to infinity, you have a thing that looks like this. Now, this is new notation for you. You don't have to know this. The limit as x goes to infinity. So we're letting x get really, really big here. But we're also letting, wait a minute. This is 1 over x. That looks better. Sorry. That was bad. This is 1 over x. Sorry about that. So that this is a fraction, so is this. This is r over n, this is 1 over x, this is x, this is nt. Yeah, but there's lots and lots of things that are similar about this. If you let x get bigger and bigger and bigger and bigger and bigger, then doesn't this number right here get smaller and smaller and smaller?
Yeah.
And 1 plus something extremely small is just barely more than 1. However, you're taking something barely more than 1 as long as it's larger than 1, remember? And raising it this many times, we're letting x go. Letting x go to infinity is making this number get really small, but it's making this number get, well, it's not really, really, really big because this is getting smaller and you're exponenting something closer and closer and closer to 1, but you're exponenting it more and more and more and more and more times. If that happens, and I don't expect you to understand all of that and imagine what's happening, but if you do that, you get e. Okay, that's how the number e is generated, 2.718. And so when we talk about something like this right here, and all of this right here, this part went to e, then what you end up with is p e to the RT instead. That's where your interest rate comes in. This is compounding periodically, every once in a while, every quarter, every 3 months, or every day. This is compounding every single instant of time. And you might think that would make your money grow really, really, really fast. It doesn't. The difference between doing this and doing this quarterly over about 10 years is a very, very small amount. But this is a little more. The more often you compound, the more you get. But not by much. So this is compounding continuously. You will see this on your exercises today. This is compounding continuously. This is compounding periodically. This P and this P, don't get those confused. Periodically just means that n is a number that you can identify. It's not going to infinity. Periodically, this is what you do if you're compounding periodically. If you compound continuously, this is the formula used. P in both cases is the principal investment. Okay. Now, other things that grow continuously, especially if you got a whole bunch of them, are things like the population of the earth or even the population of the United States. Those grow in a natural way, naturally. And when you have naturally growing anything or naturally decaying anything, you think the number E. Okay, it's a natural growth base for an exponent. So take a look at example 1. Let's see if we can make some things work here. What they're trying to do in example 1 is get you used to seeing E in a problem and getting you to understand that even if it is a base of an exponent, it still behaves like all exponents do. So I'm going to erase all of this so I can stay on camera. And we're going to take a look at things like, for example 1, I have e to the 3 times e to the 6. What do you suppose that is?
E to the 9.
E to the 9. They behave just like any other exponent you've ever done. E is not a variable though, folks. E is not a variable. It's a constant, like pi. It looks like a variable because it's a letter, but it's not. It's a constant. Okay? And now, take a look at the B part so that I can hurry through this. I'm going to put this all on the board. The B part says 16e to the 5th over 4e to the 4th. What does that reduce to?
4e to the 9.
4e to the
E.
1, which is e. It's just 4e. Everybody clear? Okay. On the next one, what do you suppose that's going to be? Now be careful. 9 over e to the 8x.
Oh, yeah, that makes sense, yeah.
Because it's
E, so just so you didn't follow that, it's 3e to the negative 4x squared. 3e to the 4x, negative 4x squared. Okay. Don't forget that the 2 here has to apply to the 3 and the e applies to the 3 is 3 squared, which is 9. If I multiply, because the exponent here times this, I multiply exponents when they're stacked up like that, and I get e to the negative 8x. But that really ought to go downstairs so we can be positive. We get 9 over e to the 8x. Okay? Did y'all follow? So they're just trying to get you convinced and get your feet wet here a little bit and say E behaves like all exponents do. Okay, moving on. Would you look at the top of page 305? Because we're talking about the difference, it's not much of a difference. If I have, like yesterday, a b to the x, and today, a e to the x, I know you're not thinking much different, and they are much different. In the graph, if b is a positive number, if b is greater than 1, it's going to go like that. Well, e is greater than 1. So when e grows, it always goes up like that. I know, you're going, they look exactly alike. They are slightly different depending on what b is. If this is 2 and this is 2.718, they're very much alike. If this is 10 and this is 2.718, this one, if this is a 10 right here, is going to grow like that compared to that. It's going to go up faster because it's the base. You're using 10 over and over and over. Here you're using about 3 over and over. It's small, it doesn't grow as fast. They have the same basic shape, is what we're saying. How could you make, what do you think about this? How could you make this? What could you do to this to make it a decay?
Negative exponent.
What negative?
Put it on the outside, so
Negative.
it reflect in the line. Or is it negative?
A negative e.
It just be negative.
Okay, just a minute. Wait. Just hold on a minute.
You can't.
Shh. Yes, you can. We can make it do that. But I want you to think about what causes this. When we have something like this, you can have a growth if b is what? Not positive. Greater than 1. If I have a decay from yesterday's equation, it comes down like that. That means that b is between 0 and 1, right?
Yeah.
So you look at this, you go, but e is a constant. E is 2.718, which is clearly greater than 1. So you'd always get a growth. No. Some of you were saying, if this was negative, like this, isn't that the same thing as 1 over e to the positive x?
Yeah.
Now listen, stay with me. Isn't that the same as a times 1 over e to the x?
Oh, yeah.
Because look, 1, you're going, but there's no x on this. Well, if you really wanted to, this as 1 to the x. Nobody does that because 1 to the anything is 1, so we don't bother writing the x above it. But you could, and it would still be the same value, right? So I could extract that x that I used on both of these out to the top again right here and write it like this. And because of that, I have 1 over 2.718, which is less than 1. This is a decay. This is a decay. So if you just have AE to the something and the something is negative, this is the reason why it makes it a decay, is because what you'll be powering is 1 over E to the something.
Question, how come you don't put it like underneath the A?
Because the X doesn't belong to the A. The A is just hanging out there. The only thing X belongs to is the E. It would have to have parentheses for X to belong to the A as well. It's a good question. So do you see that if you have this and X is, and let's say we have this, it said X is greater than 0, you're guaranteed to have a growth model. But if you have this, well, you're not going to like this. See if you can make your mind do these flip-flops. If you have this and X is greater than 0, you have a decay. You're going, what? This guarantees that this exponent is positive, so I have a positive to a positive, positive, something greater than 1. So this will be a growth. This says if X is positive, but we make it negative in the writing, then we've got a decay. Because if I had said this, then I would have a negative negative. See what I mean? Now if I have this, now I've got a decay again because this is guaranteed to be negative. You've got to watch your signs real carefully. This generally means we mean this to be a negative number. So don't let that bother you too much. But you may have to pay attention to that a couple times. Make sure that you understand that if X is less than 0 and it's already negative, you have a negative negative. It's weird stuff. And it's very subtle. Okay. Moving on. Only one more example. Yay. So the main theme here so far is, yeah, we got this weird number E, it's irrational, it's kind of bizarre, it has to do with natural growth. But the nice thing is it behaves the way all exponents behave, and you know how that is, so it's not gonna be that big a deal. Okay, look at example 3. And it says, you and your friend each have accounts that earn annual interest compounded continuously. Oh, compounded continuously. Remember what that is? Better get it in your head for test time. What's compounded continuously? This is the amount of money in your account is equal to PE to the RT. Most people, if you can remember where things go, it's just A equals per. Okay, so let's see if we can figure out how this goes. It says you and your friend each have accounts that earn annual interest compounded continuously. So that's our formula. It says the balance A in dollars of your account after T years can be modeled by 4,500 E to the 0.4T. 0.04T. 4,500 I said? Is that what I said? E to the 0.04 T. Okay, based on what you see here, what was the principal investment? 4,500. What's the interest rate? 4% per year. Can you all read that from this based on what this is R as a decimal, so it's 4%. P is still P, it's 4,500. So we took 4,500 to the bank, it grew at 4% per year, compounded every instant of time, continuously. Okay, now here comes the clincher. Pay attention now, because you're gonna have to do this not only in this exercise, you'll have to do it on the test, and you'll have to do it on your ISAT test, very likely in the spring, if you're a sophomore. Okay, they love this kind of stuff where you have two different representations of something and you have to be able to compare. So listen up. It says the graph to the left there. The graph shows the balance of your friend's account over time. The question is, which account has a greater principal? What's your friend's investment? Can you read the graph for that? What's your friend's principal investment?
4,000.
4,000. Can you read that from the graph, everybody? Y'all see where we're getting that from? And what was our principal investment?
4,500.
So we have the bigger amount in the bank to begin with. Is that right?
Yep.
Okay. Now it asks, which has a greater balance after 10 years? Well, look at the graph. Take your eyeballs out on the x-axis to 10 years. Can you all find the 10 marker? It's not marked. Between 8 and 12, duh. Y'all see it?
Yep.
Go up to the graph and estimate for me about what the account balance is.
7,200.
Okay, all right, I'll put that, 7,200. What's our account balance after 10 years?
6713.
What?
6713.
Because you got that from the solution?
Yeah.
Well, how can you figure it out? You don't look at solutions to find solutions. How do you figure out our balance after 10 years?
Put 10 in for T.
Yeah, you've got to crank this out, putting 10 in for T. So ours is found out by looking at the equation and plugging something in. Balances and principles and stuff like that are found there by looking at the graph. What was our balance again?
6713.
So A equals 4,500 E to the 0.04 times 10 was 67 what?
13.
Okay, so who has the greater balance after 10 years? They do. How could that be? How could you take more money in and they make more money?
Yeah.
Yeah, their interest rate is different. That's the one thing we don't know, but we know it's better than ours. Because they started with less money and made more after 10 years. And the only way that can be accounted for is if they're both compounded continuously, is if this interest rate is bigger for them. So we don't know what the rate is, but we know it's more than 0.04. Everybody okay with that? See what's going on? All right, this exercise won't be very hard and it won't take you very long. Those of you doing it on paper, here is your sign. Don't forget, if you scored less than 75, you're doing it on paper if you want credit. Okay? So, I'll wait for you to get some paper out so to write with so everybody can write it down without me repeating. Are you ready?
Yeah.
Anybody need more time to get the paper out? Here goes. This is section 6.2, numbers 1, 2, 3 through 21 odd, 23 to 26, and 27 to 33 odd. tiny chunks. It's 20 problems, it's not gonna kill you. You'll be fine. You might even get it done before you're done if you do it on a rate of about 1 problem per minute.
Oh, okay.